Hello and welcome back again. Today we'll start with chapter 2 about complex integration. Okay, there will be three sections. First section, line integrals. So we shall start by reviewing some concepts that you probably learned last year. In the next section, section 2.2, we'll prove several important results about holomorphic functions, one of them being that a holomorphic function on an open set is analytic there. And in the last section, we'll prove a general formula, the homotopic version of Cauchy's theorem. Okay, so let us start with some review. If omega is a subset of the complex plane, a path in omega is just a continuous function from some interval alpha beta of the real line into omega. Okay, so you can think, there are several ways to think of a path, okay? And we will distinguish between path and curve, okay? So the first point of view is that a path is a deformation of, a continuous deformation of a straight line segment of the real line, okay? So, but the requirement of continuity means that we can bend the segment line, we can stretch it, we can squeeze it, but we are not allowed to break it. Okay, so this is the meaning of continuity. Okay, so it's a deformation of a straight line segment. A path is a deformation. Okay, and the second point of view that you can think of is a physical interpretation. So a path can be thought of as the motion of a particle moving between 2 points, moving between the endpoints of the path. So so gamma alpha and gamma beta are called the endpoints of the path. Gamma alpha is called the initial point, and gamma beta is the final point. Okay, so you can imagine a particle moving from gamma alpha to gamma beta as time goes from alpha to beta. Okay. Now, the image of a path, which will denote by gamma star. So gamma star is just gamma of alpha beta. This is what we draw here. Okay, so we'll distinguish. There are no universal agreement among mathematicians on the distinction between path and curve. Sometimes they are used interchangeably, but this is not a big deal. But we have to pay attention that the difference, when we have a path gives an orientation to the curve. Okay, so there are two orientations actually. We can go from gamma alpha to gamma beta or vice versa. And this is very important in integration, because if you reverse the orientation, the integral becomes opposite. Okay, so orientation is very important here. Okay, so you can think also of a curve as being, so a path can be thought of as an oriented curve. Okay, this is what is important here. Okay. Okay. Now, a piecewise smooth path is a path actually which is continuous, but it has a continuous derivative on some parts of the interval alpha beta. So we say that a path is smooth, is piecewise smooth, or just smooth. Yeah. So if it has a derivative, continuous derivative on each sub-interval of the interval alpha beta. So we can allow for the curve to have corners or even cusps. Okay. And most of the time, we shall assume that all the paths are piecewise smooth, okay, or piecewise C1, if you like. Okay, and now I'll give other examples. Okay. In algebraic topology, only continuity is assumed. Okay, they don't need the smoothness of the path. In this course, we shall need it in order to define the integral over a path. Okay, so we need more than continuity. Okay, so this is what I said. So the derivative of a path exists except at finitely many points. Okay. Now, a loop or a closed path is a path whose initial and final point coincide. Okay. So here are some typical examples of loops. So a triangle is a loop, right? Half of a circle followed by the diameter is also a loop. Okay, you can start from any point actually. You can start from here or from here, or okay. And this asteroid is also a piecewise smooth loop actually. Okay, all these are so note that we allow corners and we allow cusps. Okay, so in geometry, this shape or these shapes are not considered to be one-dimensional manifolds, but in this course they are perfectly acceptable. Okay, so according to our definition, actually this asteroid is even C1 and C infinity. Okay, although it has no tangent here, it has cusps. And by the way, do you know any formula for this asteroid? You should have encountered it in previous courses. Okay, the formula is very simple actually. Try to guess it. Okay, so all these loops are perfectly acceptable in our course. Okay. Now, if you have an oriented curve, it may have different parameterizations. Okay, so gamma is also called the parameterization of the curve. Okay. So let me give an example. Consider a small arc of a circle going in this direction from -1 over radical 2, 1 over radical 2 to its symmetric. So this is an arc of a circle oriented in this way. We can find several parameterizations of that curve that conserve the orientation. So one is given by the usual cosine sign that you know. So one parameterization would be e to the I pi minus t, where t is between pi over 4 and 3 pi over 4. Now, why pi minus t and not just t? Because we start from here. So when t equal pi over 4, this is e 3 pi over 4, so we are here. And when t equal 3 pi over 4, this will become e I pi over, so we are here. Okay, so this is the clockwise orientation. Okay, so this is one orientation. So if you like, it's a minus cosine plus I sine t. Right? Now, another parameterization, because this is the graph of a function. Okay, so on the circle x squared plus y squared equal 1, if y is positive, then necessarily y equal radical of 1 minus x squared. Okay, so this first component is t, the second component is radical 1 minus t squared. And observe that we also start from this point to this point. So they have the same orientation. If I have taken e to the it, then I would have the opposite orientation. Okay, so it gives the opposite orientation. So the orientation, so the parameterization of a path is not unique, of an oriented curve is not unique. Okay, we usually choose the one which is more convenient depending on the context. Okay, second remark. We know that there is an increasing homeomorphism from the interval 0, 1 to any interval alpha beta, and it's given by a linear map of this form. Okay, so it consists of stretching or squeezing or translating the interval. Okay, and you can find the inverse function Okay, so h and h minus, so h is bijective. It's continuous. Its inverse is continuous. Okay. So if gamma is the path from transforming an interval alpha beta, then and h is this map from alpha 0, 1 to alpha beta, then the composition of these two functions, gamma of h, okay, so gamma of h is also a path because it's still continuous. Okay, and if gamma is piecewise smooth, then gamma of h is also piecewise smooth. Okay, so gamma and gamma of h actually are two parameterizations of the same curve, actually. Okay, and since h is increasing, they give the same orientation. Okay, so this is why we can always assume that our paths are defined on the standard interval 0, 1. Okay, and this is what is done in algebraic topology. Okay, to simplify the computations, we can always assume that the domain of the path is the standard unit interval. Okay, but as we mentioned before, continuity is not enough for us. We need more than continuity. We need piecewise smoothness. Okay, because we need the derivative. Okay, in order to define the integral, as we shall see in a moment. Okay. So let us now define the line integral over a path of a continuous function. If you have a piecewise smooth path, gamma, then we know that if it's piecewise smooth, then there is a subdivision T0, T1, Tn of alpha beta on such that the restriction of gamma to each subinterval is C1. Okay, so by definition, the integral of a continuous function over this path is the sum of these integral of f of gamma of t times gamma prime of t. So this is why we need piecewise smoothness, because we need to have gamma prime. So gamma prime should exist, possibly not everywhere, but we accept that it's not defined at a finite number of points. Okay, so this is by definition. If gamma is smooth, this is just the integral from alpha to beta of f gamma t times gamma prime dt. So we don't need a subdivision if the path is smooth, not just piecewise smooth. Okay? Now, this is the definition, but it's not the best way to compute line integrals of a complex function. Okay? Not that we just assumed continuity. In practice, we will deal with functions which are more than continuous. We'll deal with analytic functions. Okay? But the minimum required is continuity, actually, because this is just a Riemann integral. Okay, if f is continuous, everything is continuous here. So this is just the Riemann integral of a continuous function. And we don't need the Lebesgue theory in this course. Okay? The Riemann integral is more than enough. Okay. So we shall learn later other ways to compute, more efficient ways to compute line integrals. Okay, so it's the same thing as in the Riemann integral. We don't compute usually the Riemann integral by going back to the definition. Rather, we have the fundamental theorem of calculus. Okay, so we shall learn later other ways to compute line integrals when it's possible. Okay. Now, what if instead of gamma, I take another parameterization? Is the integral the same? So, because we saw that an oriented curve can have more than one parameterization. What if you change the parameterization? If it's the same, if the parameterization gives the same orientation, then the two integrals are equal. Okay. So if we take, for example, an increasing diffeomorphism from 0, 1 to itself, okay, and if you have a piecewise smooth path gamma from 0, 1 to c, And we do this composition as we did before. So we call gamma tilde gamma of phi. Okay, it's the reparameterization, if you like. So gamma tilde is a reparameterization of gamma. Okay, so what do we have here actually? Then actually, if we have a continuous function, the integral of f along gamma is the same as the integral of f along gamma tilde. So note that here gamma and gamma tilde are both parameterizations of the same path, of the same oriented curve, if you like. Okay, why this is so? This is just a consequence of the definition and the change of variables formula for Riemann integrals. Okay, so okay, what is the integral over gamma tilde? By definition, it's the sum of all these integrals if we do the splitting as usual. Okay, and now you just replace in each integral gamma tilde by its value. Gamma tilde is gamma of phi. Okay, so gamma tilde prime by the chain rule is gamma prime of phi times phi prime. So this is just the definition. Okay, and now we can do a change of variables here. Okay, we let s equal phi of t, if you like. What we get? We get the integral from phi of tk to phi of tk plus 1 of f of gamma of s times gamma prime of s ds. And we use here the fact that phi prime is positive, and phi is increasing. Otherwise, we have to reverse the bounds here. Okay. And now what's that actually? This is just the integral over gamma of f. Okay. So otherwise stated, the line integral is independent on the parameterization, but provided the parameterization gives the same orientation to the curve. Okay, because otherwise phi is decreasing. The integral over gamma is the opposite. The integral over gamma tilde is minus the integral of over gamma. Okay, as you may check here, because if phi prime is negative, you have to reverse the orders here. Okay. Now, the length of a path, as you may know, is what actually? Is the integral, is the Riemann integral from alpha to beta to the modulus of gamma prime. Okay, remember that gamma prime is a complex number, so this is the modulus here. In principle, you encountered this formula before, and we can justify this formula. Where does it come from, actually? It comes from the fact that if we have a piecewise smooth path, gamma, we can approximate it by a polygonal line, and then we let the subdivision tend to infinity. Okay, so we get at the limit this integral. Okay, so such things are usually done in first or second year. Okay, so this is the length of a path. And in principle, you have proved this estimate last year. The modulus of the integral is less than the length of the path on which I'm integrating times the maximum. This is also a maximum because if f, usually f is continuous and gamma star is compact, so this is just a maximum. And this is really a fundamental estimate that you shall use in practice on the exercises. Okay? And it's not difficult to prove, actually. You can just go back to the definition. Okay? Fine. And so as a corollary of this fundamental estimate, I have the following theorem. If Fn is a sequence of continuous functions that converges uniformly on the curve gamma, then we can interchange the limit and the integral. Okay, so this is as in the usual Riemann integral. We can interchange the orders or the two operations provided you have uniform conversions. Okay, and if you have a series that converges uniformly, then we can integrate term by term. Okay, so these are just something equivalent to the usual theorems of the Riemann integral. Okay, now this is not difficult to prove. If we want to prove A actually follows from the estimate, the fundamental estimate. When I do the difference between the integral of Fn and the integral of f and modulus, first of all, I can put everything in one side. So it's the integral of the difference, actually. And if I apply the fundamental estimate to Fn minus f, I get this, length of gamma times the maximum of the difference in modulus. Okay? So if we have uniform conversions on gamma star, then this quantity tends to 0. It's not true if we just have pointwise conversions, but it's true if we have uniform conversions. So if Fn converges uniformly to f, then this quantity tends to 0, and therefore this integral tends to this integral. Okay? And the second point actually follows from A and the linearity of the integral. Okay, because since it's just a Riemann integral, any integral actually is linear. So the integral of f plus g is the integral of f plus the integral of g. Okay, and this is probably something you have, but it's not difficult to prove. Okay, so we shall use this later. This corollary, we'll use it later. Okay, now I come to the next concept of composition or product of two paths. Suppose that we have two paths, gamma 1 and gamma 2. We can assume that they are defined on 0, 1, both. If the endpoint of the first one coincides with the initial point of the second path, we say that the paths are just juxtaposable. Yeah, and now I'll draw a figure. Okay? So this is gamma 1 and this is gamma 2. Okay, so gamma 2 starts where gamma 1 ends. So the product or the composition or sometimes the juxtaposition of these two paths is what? Is the path obtained by gluing the two paths and with the same orientation. Okay, so here this is the formula for the product that we denote by gamma 1 star gamma 2 is given by this formula. Don't worry, don't be afraid from this formula. This is the formula which is standard in algebraic topology actually. And what's the significance of it? Okay, consider the interpretation of a path as being the motion of a particle along a curve. Okay, so gamma 1 maps the interval 0, 1 into this curve here with this orientation. Okay, now suppose that a particle starts here and moves at a double speed from this point to this point. Then this is just gamma 1 of 2t. Okay, so suppose that time goes from 0 to 1. I divide into two equal parts. From 0 to 1, I move at double speed, as the usual speed, along this curve. Okay, and then I move also as the double speed along the second one. And this is just gamma 2 of 2t minus 1. Okay, so 2t, it's actually the doubling of time. So time is, if you like, is contracted. Okay, and if t is between 0 and 1/2, 2t is between 0 and 1. And if t is between 1/2 and 1, then 2t minus 1 is also between 0 and 1. Okay, now this formula makes sense only if gamma 1 of 1 is equal to gamma 2 of 0, because when t equal 1/2, this is gamma 1 of 1, and this is gamma 2 of 0. They should be equal in order to get a continuous function. Otherwise, it's continuous. Actually, you know that by the pasting lemma in topology, because we are just gluing together two continuous maps that agree on the common intersection. Okay? So this is the interpretation of gamma 1 star gamma 2. We go first along gamma 1, and then we go along gamma 2. Okay? We will not use this formula, actually, but you should know it, and it's fundamental in algebraic topology. In practice, we use this rule. If gamma 1 and gamma 2 are juxtaposable paths, then the integral along the product, or the composition, is the sum of the integral over gamma 1 and the integral over gamma 2. Okay, and this is actually something that is very straightforward to see, and probably you know that. This is actually how, in practice, you compute integrals along complicated paths. Okay, we split them into small pieces and we integrate along each one, and then we do the summation. Okay. So this is a practical rule. If you want to compute the integral, okay, and recall also that, as we said, a path gives an orientation to the curve. So a curve has two orientations. One given by gamma. The opposite path actually is denoted by gamma minus, and it's defined by this formula. So if gamma goes from gamma alpha to gamma beta, when t equal alpha, we get what? We get gamma of beta. So we start from the final point. And when t equal beta, we are in alpha. Okay? So gamma minus is just the opposite path of gamma. It's given by this formula. Okay? And now, as you observed, actually, when we reverse the orientation, or when you integrate along the opposite path, the integral becomes opposite, becomes the opposite of the integral. Okay, so this is why orientation is very important. Okay, and also this is not difficult to prove. Just go back to the definition. Okay, so this concludes the first part of section 2.1. I think it's enough for today. In the next video, we shall introduce other ways to compute line integrals, and when this is possible, and we shall introduce the concept of the antiderivative of a function. Okay, so I will stop here and we continue next time.